All right, last topic in the unit. Now, something like example 1 here, we look at this is troublesome. Like right off the bat, you look at this and it's troublesome, because the last problem that we did on the previous page had a trinomial in the denominator, but that was a trig substitution or a shortcut rule. But now all of a sudden, it's part of this topic called partial fraction decomposition. All right, so how do you recognize the difference? Well, the key ingredient is, first and foremost, a radical. If you don't see a radical in it, then odds are you're not required to do trig substitution, right? If there's no radical in it, you still can opt to do a trig substitution. Like, you can choose to do it. Like, for example, on the test tomorrow, you're presented with a problem that based on the breakdown is supposed to be a partial fraction question. But you look at this and say, I can do this with a trig substitution, so I'm just going to do it that way. Right? The best way to do it would be with partial fractions, but you could technically do it with a trig substitution. Right? So that would be your choice. In this case, what we're looking at is a fraction that has no radicals. It's just a polynomial fraction, aka a rational function. All right, so the big question would be, well, how do I know that this is something that I would use this technique called partial fraction decomposition? The first indicator that I would look for is whether or not the denominator is factorable. All right, and if it's not, it still could be partial fractions, but odds are you're going to be looking for a different approach. All right, so x plus 5x minus 2. All right, but don't stop there. See if it's factorable in such a way that one of the factors cancels with the numerator. I mean, that's the best case scenario, because then everything cleans up nicely. Right? Maybe it all cancels down to like a 2, and then you're just like, oh, 2x, final answer, done. Right? So we factored it. It turned out that we have linear factors and we have some numerator. What happened here, and this is the main idea behind partial fractions. You remember back in algebra 1, college algebra, whatever, and then if you're thinking high school, you did it a little bit in algebra 1, but then you did it a whole lot more in algebra 2. The idea of getting common denominators with algebraic expressions. You got the common denominators, and then you had to combine the numerators, but then once you did that, you then had to factor the numerators, and then use that to cancel and simplify. And then eventually you got usually some simple expression like x minus 3 over x plus 2 or something like that. But every now and then, you got some expression like 4x plus 41 over x plus 5x minus 2. And you're like, oh, clearly I did something wrong. You didn't do anything wrong. That was just the answer. All right. The reason I'm bringing this up is because each one of these questions is the result of that process. All right. So what happened was some 10th grade student in high school was given 2 algebraic fractions to add. They got a common denominator. They added their fractions together and simplified. I took their answers and made them into a question for you. All right, that's what partial fractions are. They're the result of a common denominator involving algebraic fractions. All right, so what do we have to do? We have to unget a common denominator. We want to break the fraction up into 2 separate fractions based off of a sum or difference. All right, so I don't want this as one fraction like we wanted in algebra 2. I want it as the sum of 2 or more fractions. Because if I can break it up into separate fractions, then I'll have linear factors involved. It's going to be easier to anti-differentiate in that form. All right? To the point where, like, you start questioning why you ever had to learn how to get common denominators and add these things to begin with. It's like, wait, so you're telling me that we're making more work for ourselves by getting common denominators and put it all together? Why the hell do we have to do that to begin with? Same reason you had to learn how to rationalize denominators, because it was a skill and that was the best way to teach it. right? But it's not really as useful as going the other way, right? So the big question becomes, well, how do you go the other way? Well, this table, believe it or not, well, in my opinion, anyway, it's all based off my opinion. This is the best way to kind of quantify how this approach plays out. Factors in the denominator can be linear factors. They can be linear factors raised to a power. They could be quadratic factors. They could be quadratic factors raised to powers. They could also continue on. You could have cubic, you could have quartic, or everything, but that's beyond the scope of what we're going to do here. All right. If you get the concept after linear and quadratic, you get it for everything. All right. We don't have to deal with fractional or any kind of negative powers, because if it's a fractional power, it's a root, in which case we're thinking trig substitution. If it's a negative power, if I had something like 1 over x minus 2 to the negative first, well, it's not really a fraction. That goes up top, the negative power becomes positive. It's not a denominator, it's really a numerator, right? So what this is telling me is that if you have a factor that is linear, this is what its corresponding term in the partial fraction decomposition is going to look like. All right. The whole idea behind this is to manufacture a natural log antiderivative. All right. So the way a natural log works out is if the numerator is the derivative of the denominator, then you're looking at a natural log. So for example, I have, let's say, y equals, well, I'll just say the antiderivative of 1 over x. I'll keep it very simple. Antiderivative of 1 over x. The numerator is the derivative of the denominator. All right, so that's natural log. I can give you another one. Cosine x over sine x. The numerator is the derivative of the denominator. I can go algebraic, 2x over x squared dx, but that's kind of borderline ridiculous, because that would simplify to 2 over x, pull out the 2, it's really the same thing as 1 over x. But the numerator is the derivative of the denominator, all right? A line is the derivative of a quadratic, all right? So what we want to do is, if my denominator is quadratic, make the numerator some line. If my denominator is a line, the numerator should be the derivative of a line, which is that line's slope. All right? That's the relationship. All right? So we need some function that we know would be the derivative of the denominator. That's the goal. Easier said than done. So how do we do it? First, we pretend that this isn't even a Calc 2 question. So no integral. Forget the integral. And fun fact, this is not even a Calc 2 concept. That doesn't mean it's easy. It just means that you should have learned this in pre-calc. But nobody ever teaches it in pre-calc. Like, we ran out of time, so we're going to skip it. And you're like, but there's 3 weeks left in the course. Yeah, we ran out of time. Nobody ever wants to teach it either, so. But it's not that bad, procedurally. So I have 2 factors. Each one is going to be a denominator in my expansion. All right. Now, this is the one big component. When we're deciding on what the numerators are going to be, I mean, you could technically go guess and check, and a lot of times it's going to work out, but you kind of want to stay away from that. We know that the numerators have to be some constant, right? I just don't know what the constants are. I don't want to say that it is the derivative of this denominator. The relationship is that the numerator has to be the derivative of a denominator. Right? The denominator is just a line. the derivative of a line is a slope. It's a constant. It's the relationship that we care about. But we leave it open to be any constant. All right, so how do we represent any constant? The letter A works. All right, but the second one has to be some other constant A. All right, but now I have confusion. Are they the same A or are they different A? Well, they could be different, so let's subscript them.
Could you do a B?
You can use B instead, sure. Absolutely. As long as you're distinguishing your constants from one another. All right, so I need to solve this. First thing I'm going to do, by the way, that's partial fraction decomposition right there. That's the concept. Everything after this is algebra. All right? This is the concept. So if you're good at this point, then you get it. Everything after this is just figuring out now what A1 and A2 have to be. So what I'm going to do is clear out my denominators by multiplying by x plus 5, x minus 2. That's going to give me 4x plus 41, because it would cancel on the left-hand side. We're multiplying this by each fraction. Right? You can multiply an equation by whatever you want as long as you multiply each term by that same expression or product of expressions. When I multiply these factors by the first fraction, the x plus 5s cancel out, leaving me with the A1 and x minus 2. And then for the second one, the x minus 2s are going to cancel out, leaving me with an A2 x plus 5. So we're moving in the right direction. Surprisingly. All right. Now, if you've seen this concept before, what I'm about to do might be slightly different from the way you've seen it, but my way's better, so just forget the way you did it. It's fine. I don't always say that. Most of the time I give you a choice, but I've seen the other approaches, and I was even taught the other approach, and it just seems so arbitrary. Like, just do this. Why? Because it works. I don't like that. Right? I never like that. It's algebra. We're going to perform algebra here. All right, so I'm going to distribute a sub 1x minus 2a sub 1 plus a sub 2x plus 5a sub 2. All right, now if we're going to get equality here, and honestly, I don't like other techniques like that because I can't remember, like, the steps. I can remember concepts. I can remember, like, why things, like, if I understand the underlying structure, many of you are like this. If you understand why things work the way they do, then you're not studying steps. And then if that's the case, you don't have to worry about forgetting steps. You forget steps on a test, you lose a point or 2 points. I forget steps, I make a freaking idiot out of myself in front of 33 people. All right, so that's my motivation there. Anyway, I need equality here. So what I need to have happen is a sub 1 plus a sub 2 has to be equal to 4. All right, because these are my x terms. If this is going to be an equivalent relation, then whatever a sub 1 and a sub 2 are, they have to give me a 4 as a result in order for my x's to combine to give me a 4x. So that's one equation. Another one would be all the constant stuff, right? Everything that doesn't have an x in it. Negative 2a sub 1 and 5a sub 1 have to give me the 41. I said 5a sub 1, I meant 5a sub 2. So negative 2a sub 1 plus 5a sub 2 have to give me the 41. All right, so we have a system of equation in two variables, system of equations. We just got to solve. Question?
For the purple equation, can you include the x's or should we leave them out?
You leave them out because they're going to cancel anyway. All right, so it's up to you at this point how you want to go about it. I'll show you. I always hesitate to do this because it may not be something you actually want to see, but the matrix approach on your calculators, they solve linear systems for you. And so, like, you wouldn't actually have to do this algebraically. So I'll show you how to do that very quickly. If you don't like it, then you could pretend I didn't say anything. All right, but if you do like it, then you have another skill in your arsenal. All right, it's a little precursor or a preview of linear algebra. It's a pretty cool technique. The one thing you're not going to get is any kind of real context related to it. Be like, this is one of those things where it just works. Why does it work? Well, if you take linear algebra, you'll find out. Right? Unfortunately, this is the first time in a while that I'm not teaching linear algebra in summer session 2, so sorry. You can check out my videos online. Why wouldn't I want to do that? All right, so what this amounted to, and I'll embed that video later on. We had these coefficients, 114, negative 25, 41. Using the row reduction technique, this simplified to 1, 0, what was it, negative 3, 0, 1, and 7. All right. So if you think about the variables and how they work their way into the equation, originally this was 1a1 plus 1a2 equals 4. Now this is 1a1 plus 0a2 equals negative 3. It simplified it for us. All right, I can write that down, although it's not something you would need to do. This amounts to 1a1 plus 0a2 is equal to negative 3. That's the same as saying a1 is equal to negative 3. Also, we would have 0a1 plus 1a2 is equal to 7. That's the same as saying a2 is equal to 7. Try it with any linear system of equations. If there is a solution, this process will give that to you. All right, and it's not just limited to 2 equations, 2 variables. 5 equations, 5 variables. All right, you just eliminated the need to do any algebra. All right. Okay, well, you had to do all this algebra, but any additional algebra. So now we're at the point, and like I said, I'll run through the process again for another example in a little while. But now we're at the point where I have an equivalent set of fractions that make up the same ratio that we were given, which is great news. Right? What I have now, because a1 is negative 3, negative 3 over x plus 5 plus 7 over x minus 2 dx. All right? Those are natural log antiderivatives. All right? Take a shot. You know, I mean, you can do u substitution if you want, but you use the u sub on the fly, baby u substitution. You know, make a conjecture. Take a shot. I think that the natural log of x plus 5 will get it done. And then you say, okay, well, let me think about what that would give me. 1 over x plus 5 times 1. All right, so 1 over x plus 5. Oh, wait, but I need a negative 3. All right. Boop. There it is. For the second one, take a shot. I think it's the natural log of x minus 2. So the derivative of that will be 1 over x minus 2. But I need a 7 over x minus 2. So, plus 7. Throw a plus c on at the end and you're done. All right, so the actual integration part of it should be very easy. You're doing all of this other work so that the integration part is easy. But really, if you take advantage of little shortcuts like this, you can make it even easier. All right. The setup part, like I said before, the setup part is your partial fraction decomposition. Everything after that is algebra. All right. And then even here, it's algebra, but I'm giving you the opportunity to opt out of that algebra. You don't have to do that algebra if you don't want to. Now, if there's other techniques you want to use, that's fine. All right. Solving a system of equations, a linear system, it's the same as finding the intersection between two lines. Write it as x plus y equals 4, negative 2x plus 5y equals 41. Solve them both for y, put them in your calculator, see where they cross. You'll get your solutions that way. All right, but the one thing you don't want to do is get bogged down with the algebra. All right, find some shortcuts that'll help you get the job done. All right. So the second example gets easier. You just got to look at what you have and kind of decide what you need based off of that. What I have here is a linear factor, so I'm going to rewrite. It's already in factored form, so somebody was being nice to us. Although there's usually a reckoning. If they're nice to you for one thing, they tend to make up for it in other areas, whoever they are. Those people. All right. So I have one factor here, one linear factor, x. So x on the bottom, a sub 1 on the top. Now, the other one, that's a little bit of a different story. So I'm going to go back to the table. We have another possibility is a linear factor raised to a power. And then you have all this stuff. And you're like, okay, now this is getting out of hand. All right? No, it's really not that bad. What this is telling us is that if you have a linear factor raised to a power, what you have to do is create a fraction with a constant just over the factor itself, and then every other consecutively higher power until you get to the power that's given. All right? I said that fast, and it's weird to begin with, so let me just demonstrate, and then I'll explain it again. So we have x plus 1 to the second power. So what I'm going to do is I'm going to start off with a denominator of x plus 1. And then the second fraction will have a denominator of x plus 1 to the second. All right. That's all that I'm talking about here. If this said x plus 1 to the fifth, I'd have a lot of fractions. I would start off with x plus 1, then I would have x plus 1 to the second, to the third, to the fourth, and to the fifth. So obviously you don't want anything too large in terms of exponents, because if I had something like x plus 1 to the 17th, x plus 1 to the second, to the third, to the fourth, to the fifth, all the way up to the 17th power. We would have a total of 18 fractions here that we'd have to work with. All right, it would be a complete disaster. All right, but both of these factors are linear, so each one gets a constant numerator. All right, so I already used A1, so here comes A2 and A3. So that's my partial fraction decomposition. I just have to solve for A1, 2, and 3.
Can you explain where A1 over x is coming from? Is
A1 over x is coming from the fact that this is its own unique linear factor, just like x plus 5. Just think of this as like x plus 0. If it were over here, it would be its own factor with its own numerator. All right, so I'm going to run through multiplying everything by x times x plus 1 squared. So that's going to give me 5x squared plus 20x plus 6 is equal to a sub 1. The x's would cancel, so x plus 1 squared plus a sub 2 x times x plus 1, and then a sub 3x. All right, so all that's happening here is I'm taking the common denominator, multiplying it by each term, cancels out completely on the left. Only the x would cancel out here, leaving me with the x plus 1 squared multiplied by a sub 1. Only an x plus 1 would cancel here, leaving me with an x plus 1 and an x. So that's where these two bad boys come from. And then the x plus 1 squared, that's the best case scenario, would cancel, leaving me with just an x. Now I have to distribute out. All right. Not as nice as the previous problem, but we have a nice little calculator shortcut coming up. Although I will say that in this case, you'll look at the equations we come up with and say, I don't need your calculator trick for this one, but I'll do it anyway, just so you get some more experience with it. A sub 2x plus a sub 3x. I don't know how many people are planning on taking differential equations after this course, but the biggest thing that students struggle with in that course is this concept. And it's not that you're struggling with this concept, it's that when you need to use this concept that you're supposed to already know, that you don't know, you struggle with the concept you're trying to apply it to, right? So if you could, I know it's a condensed course, we're squeezing a lot of stuff in, but before you take differential equations, if I could recommend you review one thing, it would be this concept. All right. Calc 3, it's trig. Review trig. Like a lot. So, distributing again. You're like, we're just worried about the test tomorrow. I know. All right, so big mess, but it'll clean up. It has to. Because I don't know what I'm going to do if it doesn't. All right, a sub 1 and a sub 2, those are the ones that have x squared associated with them. Those have to add to equal x squared. 5x squared. So a sub 1 plus a sub 2 should be equal to 5. The ones that have x's attached to them, those would be 2a sub 1, a sub 2, and a sub 3. Those have to add to equal to 20. And then, this is what I was talking about a few minutes ago, where I said you may not opt to use the calculator technique because there's only a lone constant, a sub 1. So that one actually has to be 6. Right, so it's like, well, I now know a sub 1, so indirectly I know a sub 2, and I could pretty easily figure out a sub 3. All right, that being said, I'm still going to show you on the calculator because it's a good skill. For those of you who are interested in it, you probably want to see it a second time around. All right, we have to take note of the different variables we have here. This is one little twist on this that may be a little weird, that we have a sub 1, 2, and 3. So every equation would need to be written in that form. So a sub 1 plus a sub 2 plus 0 a sub 3 is equal to 5. It's kind of like synthetic division, where when you were missing a term, you had to put a 0 coefficient in there. It's the same idea. So 2a sub 1 plus a sub 2 plus a sub 3 is 20. And then a sub 1 plus 0 a sub 2 plus 0 a sub 3 is going to be equal to 6. All right. Something to consider if you're on the fence as to whether or not this is a technique that you want to use. On a test, you're not writing any of this down. Like, I'm writing this down to teach you how to use the technique. You're going from these equations to a sub 1, 2, and 3 are equal to these numbers. All right. You don't even have to show me how you got there. All right. I'll be watching to make sure you're not cheating. So when you come up with a sub 1 is equal to 6, a sub 2 is equal to -1, like I'll know that you used the right technique, right? Because I would have already given you a 0 for cheating if I thought otherwise. Right? So you just write it down and enjoy the moment. All right, so what you would type into your calculator would be 1105 to 1120 1006. I'm actually going to crank it out real quick, and then I'll show you on the big screen. I just want to have the numbers to point to. Oop. All right, so therefore, a sub 1 is equal to 6, a sub 2 is equal to -1, and a sub 3 is equal to 9. So, like I said, you already knew one of the variables was equal to 6, so you're good in that if you wanted to do it by hand, you would have been fine, but it very easily could have been not the case. You know, maybe there's some fractional values involved. So, oh, and by the way, if you get a matrix consisting of all decimal values, go ahead and hit math, enter, enter. It'll convert it right to fraction form too. So it'll give you some nice values there also, even if there was fractional values, like the one that'll be on the test tomorrow. So we're looking at 6 over x plus -1 over x plus 1 plus 9 over x plus 1 squared dx. Much more integrable. The 6 over x is 6 ln x. Like I said before, take a shot. The denominator has a derivative of 1, right? So it's a natural log. But I want the negative there, so negative ln x plus 1. The only concern would be that last guy there, 9 over the x plus 1 squared dx. All right, for that, I'm just leaving it in integral form because for that one, I mean, you may want to use u substitution, but you also may want to take a shot in the dark. If your inner function has a derivative equal to 1, you could integrate around the inner function. All right, so that means I could write this as 9x plus 1 to the negative second dx, and then apply the reverse power rule as if this were just an x. Increase the exponent by 1. X plus 1 to the negative first. Divide by the new exponent, so negative 9 plus c. All right. That only works if your inner function, so if you're planning on using u substitution, pause, take a moment, think about it. That's what I was talking about before. There's a reward if you pause, take a moment, and think about it. Because if you say to yourself, well, what would be the derivative of that thing I'm about to call u? 1, I can integrate around it. All right, I could pretend it's just an x. And I don't have to worry about it. It's not going to have any impact on the derivative or antiderivative. All right.